So using linear algebra to solve um, here the current that flows through a circuit, three things that I think are useful comes from Kirchhoff's law, um, um, and they all deal with the same idea from the traffic flow. That is that energy must be conserved within the system. What goes in has to equal what comes out. So I think if you have that in mind, this is very straightforward. The first aspect of of Kirchhoff's law, which is really, if you think about it, if you look at physics, it's a copy of Newton's law, but here it is dealing with the electric flow within a circuit. Um, and then Newton's law comes out of Maxwell's law of the law of conservation of energy. So they're all basically one and the same. In differential equations, we call it an exact differential form. In vectors, we say that the system or the space is said to conserve energy, and that's what you deal with in Calculus 3. So the Calculus 3, the differential equations, and the physics, and here even the application of linear algebra are said to be an isomorphism. And that's a pretty good term for you, an isomorphism, that they're invariant, or that we're talking about the same thing. Different spaces, different structures, but it's the same thing. So the first, that the amount of current that flows through the so-called unit is said to be conserved. That is, that the sum of the current that flows in the circuit equals to the current that flows out. And so here the sum of the voltage drop, and that's basically what Kirchhoff's second law says, the sum of the voltage drops equals the sum of the voltage rising. And so we use that to apply to even an item on the grid, whether it's a capacitor, a resistor, a transformer, doesn't matter. Three things we look at. One, we look at the so-called voltage drop or the voltage rise. We look at that. And then secondly, we look at the so-called voltage drop on a resistor. Since here for this simple grid, we talk about applying linear algebra on a resistor. We look at the voltage drop on a resistor. Then we also look at the voltage rise of a resistor. And then also the voltage rise and drop on a battery. Let's deal with the battery first, because I think that's pretty easy, and it flows in terms of plus is plus, negative is negative. So if it's a battery that you're looking at, it'll have two slash marks with the plus and a negative sign on each side to denote the positive and the negative pole. The current on the loop is said to travel according, watch this, the current on the loop is said to travel in the direction that was supplied by the original creator. And it's pretty good. Okay, well, I believe that God is the original creator. And what he and how he supplied nature is how energy or electricity travels in its direction, and that direction simply clockwise. That's all I'm saying. The original supplier did that. All right. So the electric current flows clockwise. So we're going to take a loop, and you look at that loop and how the energy is traveling. The electricity, which is the energy for so-called electronic grid, is going to be traveling clockwise. So if you just take your finger and go clockwise on whatever loop you're looking at, in terms of the voltage drop, if the direction assigned to the loop, which is clockwise, and then you take the battery, if the battery poles say from negative to positive, then here we have a voltage rise. It's plus sign in front of the amount of voltage on that battery. We get the opposite if if the direction of the loop is clockwise, and then if you look at clockwise as you run on that loop, and then you get to the battery, it goes from plus negative, then it's a voltage drop. It's going to be a negative in front of the voltage, right? So if for the battery, if I'm going from negative plus sign in front of the voltage. If I'm going from plus to negative, negative sign. It's just the opposite for a resistor, because the idea of the resistor is to resist, the current that's coming through for the particular charge. So if it's resistant, it's basically given a negative resistance, right? So if that's the case, then we just flip that. So come back here to number 2, the voltage drop, that means negative, occurs at a resistor if the direction assigned to the loop here, that is I'm going clockwise, the voltage assigned to the current through the resistor is the same as the direction assigned to the loop. Well, the direction assigned to the loop is clockwise. If the direction that's assigned to the loop is the same as the direction that's assigned to the so-called resistor, it's a drop because it's a resistor, right? It's going to be negative. And we get the complete opposite. The voltage rise here, we have plus sign if the direction that's assigned to the resistor is in the opposite direction of the current that's assigned to the loop. Okay. So for the resistor, and when we determine plus or minus sign, you're going to think just opposite of how the battery operates in terms of the current on the particular grid. Okay. So resistor, think the opposite in terms of the battery. I think with these 3 things in mind, you can extract from the diagram, you can extract from that the items necessary for the matrix or for the system. So we're going to convert to a system, convert the system obviously to a matrix, solve the matrix. What am I solving for? This is a simple grid in terms of a battery or batteries and resistors. We're going to determine the charge on the resistor, how much charge is being supplied from that particular resistor on the so-called circuit. So that's our objective. Let's look. So the first problem, I wrote out here how we're going to build it. And then the second problem, I have nothing written out. We'll just start from scratch. So what we're going to look at the voltage on the circuit. Now if you look at this circuit here, and in class, they talked about you can take a node the same way how we did with the traffic flow, take that node and look at the current as it flows through that one particular node. You can let that be your reference point, and that's fine. So if you take this node down here at the bottom right here by this 6-volt battery, and then now I'm going to look in terms of the voltage that's being applied to all of the resistors. It's resistor 1, 2, and 3. So if I look at this node down here, and if I take the resistance 1, and this guy, the direction that it's flowing in with respect to this node is going in here, it's going in, but look at resistance 3, the resistor 3 is going out. So basically I have I sub 1 plus I sub 2 is equal to I sub 3. And then you can subtract I sub 3 on both sides, you get I sub 1 plus I sub 2 minus I sub 3 is equal to 0. Do you get that? Right? So you can take a node and look at that node. Matter of fact, you can do that for even the left loop, the right loop, and for the outer loop in terms of the charge that's being supplied to each loop. And you can still consider that one node there as things come here. And by all means, if you go clockwise and you can measure, it doesn't matter about taking that one node. You can look at that from any point, even this node up here. I mean, that's fine. So you get the voltage with respect to the resistors, and what I do simply, if you understand that, that's fine. I just look at the directions of the resistors, and so basically I have I sub 1, I sub 2 going in the same direction, so I get I sub 1 plus I sub 2 is equal to the opposite guy, equal to I sub 3, and you still get it, right? Now look at the left loop. We're going to break this down into the left loop, the right loop, and then the whole outer loop to build the system. So, and let me just scroll down so you can see that, but we'll talk about it and build it. So if you take the left loop, you can look at the node if you want, but I'm just going to take the whole loop itself, and so I'm going clockwise. So I'm going in that direction, and the same thing for the right loop, and then the same idea would be for the entire loop itself. But let's start with the left loop. So if I start here with the left loop, if I make this bottom node as my reference point, so if I start from there, if I go clockwise, I get to this 6-volt battery. It goes from plus to negative. That means that there's going to be a negative charge there from the battery, right? So it's -6. And then when I come to this resistor up here, there's 2 ohms assigned to it, right? But in terms of the if it's a drop or if it's a rise, we said that if the direction assigned to the loop is opposite of the direction assigned to the resistor, then here we have a voltage rise, right? Think resistors, think opposite is plus, right? Same is negative for resistor. So that's why here this is +2 I sub 1. And then if I come around, I come to this node here, it's good. Then I come down to here, this second resistor, I sub 2. Now look at this guy. So the direction of the loop and the direction of the resistor are the same, negative. So it's -2 I sub 2 equal to 0. Now let's look at the right loop. Right? I think it might be on the other page. We can talk about it, and then the write-up is fine. Oh, it's way up there. So look at the right loop. And so here we're going clockwise. So if I'm starting here at the reference point with this node, if I go this way. So look at this resistor. The direction of the loop is opposite of the direction that's assigned to this resistor. So it's going to be plus, right? So this guy's going this way, that's going that way, opposite resistor plus. So it's going to be +2 I sub 2. And then when I come here to this 8-volt, is plus going to negative, so it's going to be -8, right? And then when I get here, this guy is opposite of this guy. Did I say this was plus or negative? What did I say for this? Okay, I said what? Plus, right? It's supposed to be plus. So if I said negative, I meant to say plus. No, that's fine. Okay. I get confused too. So I just want to make sure. That's good. Because sometimes I'm still sometimes thinking about the battery, you know. So the battery is like, if I'm moving in clockwise plus negative, then it's negative, right? And then I get that sometimes mixed up in my head with the resistor, but the resistor is opposite of how the battery acts in terms of how it receives the charge. So then we come here to this 4-ohm resistor. So the direction is opposite of the assigned charge for this resistor. So it's going to be plus here, +4 I sub 3. I kind of wrote over that I sub 3. All right. So we have that. And then what about for the loop, for just the outer loop? What happens there? Oops, talk here. So we have the outer loop. So this is my reference point here. So we go from plus to negative for the voltage. So it's going to be a -6 volt, right? And then I kind of put them both together with this voltage up here. When I come around This way is plus negative, so it's negative 6 minus 8 is negative 14 volt, right? So I put that guy there. We come to I sub 1, and the current assigned to the loop is moving opposite of the current assigned to the resistor. So it's going to be a plus 2 I sub 1. Right? Then I come around to I sub 3. Again, it's opposite. So it's going to be plus 4 I sub 3. We're going to take 1, 2, 3, 4, 3 of these statements here, and we're going to write the matrix. So the first guy is going to be, and they're all in terms of the resistor. Here, the constant, which represents the voltage on the battery, will be assigned to the right side of the matrix or the equation. So this is 1, 1, negative 1, 0. I sub 1 is 2. I sub 2 is negative 2, and then this is 0 and 6. For the right loop, there's no I sub 1. There's I sub 2, which is 2. I sub 3 is 4, and then it's equal to 14. Oh, I think I was writing. No. That's equal to 8. I think I was looking at the outer loop. Let me go back to that. This is 2 and 4. That's good. Yep. And then for the outer one, it's I sub 1 is 2. I sub 2 is 0. I sub 3 is 4. And then that's equal to 14. Now we have a matrix that we just solved. Now, what's interesting is that, before this section, basically all we've been given is either a system or a matrix, and we just ask you to solve it, and you get the solution. So now we put information before all of that, and you see how the information from the data is extracted to be placed in a matrix, and then you solve the matrix. And that's typically how life would be anyway, right? That whatever your job specification is, if it's an analysis, mathematics, computer science or engineering, you're given data. Can you extract that data to be put into some meaningful format? Here, our format is the matrix, right? So now we solve. And so we do what we know to do with a matrix. So what I'm going to do here is I'm going to add row 3 to row 2. Two, 0, 4, 14, 0, 2, 4, and 8, 2, 0, 4, 14. Now I did that because I saw a connection between row 2 and row 4. Now if I negate row 2, add that to row 4, all of row 4 goes out. Now you may say, well, what if I don't have that kind of eye? What if I don't see that? It doesn't matter. If you apply the techniques how we had taught you in terms of getting the 1 at A11, getting zeros below that, move to the second column and get the 1 at A22, get zeros above and below that, everything will still work out the same in the end, okay? Since I'm the teacher, I have God's eye. What was that movie? You remember this movie? This guy. It was like some Marvel comic, whatever movie, but this could have been Marvel comic. I don't know. We watched so many movies, but this guy, he was a bad guy, but he was African, and he said, "Get me God's eye." Like I said, get me God's eye. Apparently, is this artificial intelligence computer that is hooked up to everything in the world and all the satellites and all that. And so you just put the person's ID information in there, and it can track that person anywhere in the world, and you can see, what they're doing. And the good guy, I forget who this was, he was like, we can't allow this to get into the hands of bad people because they're just, And so this one bad guy, this dude from Africa, he had gotten it, and he was like, he could do everything with it. So he told the guy on the computer, get me God's eyes so I can see what's going on. Was that the fast? Okay, thank you. I can't remember some of the names of these movies. The Fast and the Furious. That's pretty cool, man. Get me God's eye. Oh man. Anyway. 204 1402. Huh? Still don't understand why it does that. These computers are not the best thing in the world. It's 2480000. Now what I'm going to do is just reduce the numbers. And that is, I'm going to say 1/2 times row 2 and 1/2 times row 3. We don't need that bottom row of zeros anymore. It has no significance. So now, what I want to do is to take. You can take this leading one to get a 0 there, or you can take this one and get a 0 above it, and then just swap out the rows. That's what I'm going to do. So negative row 2 plus row 1. Why do I do that? Well, there's a 0 already here, so I want to just make advantage of that 0. So now I can swap out rows 1 and 2. Now we'll use this one at A22 to get a 0 below it. Becomes a 5, becomes 7, 4, 11. So now we divide the 5, row 3 that is, by 5, or multiply by 1/5. So now we're going to take the 1 at A33 and get zeros above it. So negative 2, row 3, plus row 1, and then 3 times row 3 plus row 2. Well, it gives us what we're looking for here, and then the work is on the other side. Well, that 11/5 stays the same. So the first thing we said was negative 2 times 11/5 plus 7. So negative 2 times 11 over 5 plus a 7. So that's negative 22 over 5 plus 35 over 5. And so that gives us 13 over 5. Now for the other one, it's 3 times 11 over 5 minus 7. So 3 times 11 over 5 minus 35 over 5. So this gives us, looks like negative 33, well, positive 33 minus 35 all over 5. So we get negative 2 over 5. So what that implies is that the charge that's being supplied by the first resistance, I sub 1, is 13 over 5 ohms. Here, that second resistance, it has negative resistance there, negative 2/5 ohms. And then I sub 3, 11 over 5 ohms. Okay. Any questions? Yes, sir.
Do we need all four equations?
That's a good question. Yeah, yes and no. Is it possible to work the system without one of the equations? In the past, I have done that. There's one equation that I thought was not necessary, which is the very first one. I think it was I sub 1 plus I sub 2 minus I sub 3 equal to 0. Depending on how large the grid is, the circuit is, that guy is necessary later on. So I've seen some where we had like 5 or 6 variables out there. It was necessary. And what I'm saying is, I've worked them both ways. For this problem, I worked it without using that equation. It worked out just fine. But then I worked another problem that was like a 4x4 or 5x5, and it was necessary. Yep. Yes, sir. So no, I've been there, played around with it, and trying to cut some corners. Let's look at another one. All right. Let's take this one. So if I take this node over here, and then I see what's going in is equal to what goes out in terms of the resistors by themselves. So what I have here is I sub 1 is equal to I sub 2 plus I sub 3. The ones that have the same direction we put together. So it's equal to I sub 2 plus I sub 3. So that is I sub 1 minus I sub 2 minus I sub 3 is equal to 0. Now, if we take the top loop, the bottom, and then we take the outer as well. So if we look at the top, so the top loop, so start from this node here. If we go, we're going to travel clockwise. So if we travel clockwise, we come here to this first resistance. It's traveling opposite of the assigned current flow through the circuit. So it's going to be a plus here. So we just say 4 I sub 2. We come to this voltage. Here it's dropping, so it's going from plus to negative, so it's minus 4. Come to this voltage, plus to negative, it's also dropping, minus 5. I come to this resistance here, which is applied with 3 ohms here on it. So when I come here, it's traveling the direction of it is opposite the direction for the loop, so it's going to be a plus here, 3 times I sub 1. That's going to be equal to 0, right? What about the bottom? So the bottom, start here at this node, we travel clockwise. I come first to this resistance. It's going opposite of the direction of the loop, so this is plus 5 I sub 3. This voltage here is dropping on the battery, so this is minus 3. Here, the battery here on the bottom is going to have a rise because it's going from negative to plus, so it's just plus 4. Then I come here to this resistance. It's traveling the same direction as what's assigned here in the loop, so this is going to be negative 4 I sub 2 is equal to 0. And then we consider the outer loop. So for the outer loop, start here. We go around. So here, this is plus 5 I sub 3. The voltage on the battery drops. Minus 3. We come to this voltage here, the 5 volt. It's dropping. Minus 5. We come to this resistor, I sub 1. It's opposite. So here, it's rising. So plus 3 I sub 1 is equal to 0. Right? So we take that information and we want to be able to format our matrix. And then we solve the matrix. Let's see. Put it here. So the first line is 1, negative 1, negative 1, 0. The next one, let's find I sub 1 is 3. I sub 2 is 4. There's no I sub 3, 0. This is minus 9, but move that to the right side, it becomes positive 9. Then for the bottom loop, there's no I sub 1. There's an I sub 2 is negative 4. I sub 3 is 5. And then this is plus 1. On the right side is negative 1. Here, I sub 1 is 3. There's no I sub 2. I sub 3 is 5. And this becomes positive 8 on this side. Is everybody with me so far? Okay. So now we just solve this matrix. So notice that it looks like row 2 and row 4 have some commonality when I combine the row 3 and row 2 together. So let's try that. Just the same trick that I did for the previous problem. Looks like it matches up here too. So we'll say row 3 plus row 2. This is 3, 0, 5, and 8. 0, negative 4, 5, negative 1. 3, 0, 5, and 8. So now let's say negative row 2 plus row 4. And row 4 goes to 0. Have you all seen The Magnificent Seven yet?
It was really good, but the ending let it down, in my opinion.
Oh, yeah? Well, I thought it was good. But yeah, the ending wasn't as impactful, if that's a word, as the rest of the flow of the movie. But it was a good movie. If you haven't seen it, go see it. See it first, and then we'll talk about it. I hate to tell you something about the movie you hadn't seen it yet, right? But what was the big guy's name? He had the knife. He had a low voice, like, okay, I was just thinking.
His name, but he was awesome.
You got to see the movie. Anyway, didn't mean for that to come out, but I thought it was pretty cool. So here, 3, 0, 5, 8, 0, negative 4, 5, negative 1, 0, 0, 0, 0. All right. So let's rewrite what we have. 1, negative 1, negative 1, 0, just with the three equations. All right. So we're going to use A11 to get a 0 below it. So this becomes 3. Becomes 3 plus 5, 8. And that's still 8 there. So 0, negative 4, 5, negative 1. All right. I need to have a 1 at A22. Well, I can get a negative 1 there right now by just adding row 3 to row 2. And then we could just negate that result and we get our positive 1. All right, so negate row 2. So now we add row 2 to row 1. And then 4 times row 2 plus row 3. Squeeze in row 2, it stays the same. So we just simply add row 2 to row 1. So we got negative 52 and 5. It's negative 47. We get negative 29. So now we multiply row 3 by negative 1 over 47. All right. So it looks like we say negative, well, not a negative, positive 14 times row 3 plus row 1, and then positive 13 times row 3 plus row 2 should give us what we want. It gives us the identity matrix here, but there's some work on the other side. So the first thing we said was 14 times the 29 over 47, and then that's going to be minus 7. $77 over 47. And then the next thing to do is 13 times 29 over 47 minus 7. We get 48 over 47. Okay. Is that what you got too? Or are you trusting blind Ernest? I thought I had pink eye yesterday. Went to the doctor, and it's not pink eye. Because if you're like me, you say, "Oh, I can't be around you." It was it's an infection from allergies, just allergies. And the doctor tends to think that it was probably the contact lenses themselves. I get the ones that you throw away every 30 days, but like in maybe 15, 20 days into wearing them, they start irritating my eyes really bad. So the doctor gave me some stuff that you drop the contacts in with the enzymes and that kind of thing. And my eyes are very sensitive, so hopefully that'll work. But I'm kind of laying low on the contact lenses for a little while. So anyway, I sub 1 has a resistance of 77 over 47 ohms. I sub 2, 48 over 47 ohms. And then I sub 3, 29 over 47 ohms. Any questions? Yes, sir.
Just use the should it be current instead of amperes instead of resistance?
What was,
I know it's
what was that again?
it'd be amps instead of ohms. This is I understand that it's only like 77, it's like 7 feet resistance.
Yeah, I don't have my.
How do you do it in that?
I thought it was going to be in ohms. Yes.
Yeah, but I thought
Yeah. Right.
isn't that what we're starting?
Yeah. Yeah. Where's the? You have anybody have a book? What edition are we using? The 11th. Is that the 11th edition? Okay. What number is that? Yeah, it should be 1 point.
I mean, it's
You know, yeah, I think.
figured since we're determining current.
No, you're exactly right. It's in this section here. Let's see, where's that problem? This was number. Looks like number 8. But, is it okay? Well, this was 1.9. This is the. I think this is the current one.
It's really not.
No, I don't know what the heck I was thinking. You're exactly right. Yes, sir, it is an amperage. Sorry about that. I don't know why I'm writing ohms. Who has, was it Matthew, do you have my, I gotta take my instructor points from me today, man. I'm in a third world. Bless you, my friend.
I'm sorry for breaking that up.
No, man. Yeah, I'm getting thrown off with everything but the right thing, right? Okay, bless you. Yes, amps, folks. Hadn't been wrong since 1979. No, I'm just joking. And that's going to be the same thing for up above as well. What was that previous problem? I don't know how I got off on that.
This way.
Yes.
I learned to do these a little differently in Dr. Wilkins' classes. You did everything clockwise, and how I learned to do it.
It's counter.
You can do it any way, whatever loop, the same way, as long as your signs are right. So would you like count off on a test if I
It,
did it?
it'll still be consistent because basically all of your signs will be opposite,
Right.
and it'll still be an equivalent form. That's fine. That's fine. Yes, sir. Yeah, that'll be good. Thank you. Let's look at the next situation, how to use linear algebra to balance a chemical equation. I must say, a lot of these, you can probably just do them straightforward as you were taught, in chemistry, and that's fine. I have seen, of which I wouldn't do this to you on the test, I have seen very huge chemical equations where a little bit of linear algebra is definitely, helpful. As a matter of fact, it's more helpful if if you had a large system and you took these terms and you place those into a matrix, and then you just use a graphing utility to solve it. I mean, that's ideal as well. Here, we'll try to keep them as straightforward as possible, no more than a 2x2 or a 3x3 that we use. Here's an example. If you're given this chemical reaction, is it possible to take linear algebra to solve? All we're going to do is, for each chemical combine, just going to put a variable in front of it, and we just list them. So for the first one, we just put x sub 1. For the second one, for here, we'll put x sub 2. For the carbon dioxide, we'll put x sub 3. For the water, we'll put x sub 4. Now, when we do that, just take the elements from each one. So we got carbon, we got hydrogen, we got oxygen operating here. So I take carbon, I look at its left side and right side. What's going in, what's coming out has to equal. So it's still using that same idea that the system must be conserved. So for the carbon, I look at, now I assign this first term x sub 1. So look at the carbon here, and I count how many do I have there. I have 3, right? So I'm going to say 3 times x sub 1. I don't have any other carbon over here. It's equal to, I look at x sub 3, I have a carbon there, I only have 1. So 1 x sub 3. Now I go to the second element, oxygen. So for oxygen, look at its left side and right side, input, output. So I have 8 of these guys will assign x sub 1, 8 x sub 1, equal to, on the right side here, we assign this guy x sub 4, so it's going to be 2 of those guys times x sub 4. And then lastly, we have the oxygen. So here, there were 2 of these guys. This is assigned x sub 2. So it's going to be 2 times x sub 2 is equal to 2 times x sub 3 plus x sub 4 for the oxygen. You take this and we transpose the system into a matrix. Now to solve the matrix. Once you solve the matrix, you're determining x sub 1, x sub 2, x sub 3, x sub 4, and then from there you can be able to number how many of the elements, how much do you have within this chemical reaction, right? So let's see. So we have 4 variables, x1, x2, x3, x4, and so we're going to have a system. Here we only have 3 equations because we only have 3 elements there, right? 4 unknowns. So this is 3x sub 1. For the first row, there's no x sub 2, minus x sub 3. There's no x sub 4, equal to 0. For the second row, it's going to be 8x sub 1, no x sub 2, no x sub 3, 0, 0, minus 2x sub 4 equal to 0. And then for the last equation, or the last row, here, there's no x sub 1. Right. Yep. So let me rewrite this and write it correctly. I think I can put that in here. Will it let me? There it is. So here, that's zero. Then x sub 2 is 2. X sub 3 is negative 2. X sub 4 is it's going to be a negative 1. Okay. So now we solve this. That's better. So if you look at that, looks like we need to get a 1 here at A11. So let's go ahead and do that. So we'll say 1/3 times row 1. And since the 8 and the negative 2 have a commonality, let's go ahead and reduce that while we were there. I'm sorry. Make the numbers as small as we can. Helps us out on simplification. Okay. Let's take A11 to get a 0 below it. So negative 4 times row 1 plus row 2. 1, 0, negative 1/3, 0, and 0, 0, 0. This becomes 4/3. This stays negative 1. This is 0, 0, 2, negative 2, negative 1, 0. Right? Now I'm going to interchange rows 2 and 3. So here we'll get our 1 at A22. So column 1 is fine. Column 2 is fine. So now we have to get a 1 here at the A33 and get zeros above it and then simplify the system from there. So let's do this. Let's say 3/4 times row 3. So now just add row 3 to row 2. And then we'll say 1/3 times row 3 plus row 1. And then from there, now let me ask you this. If you have 4 unknowns and 3 equations, what type of solution are we going to get? 4 unknowns and 3 equations. Infinitely many, right? Good. So you kind of know what to be expected. So row 3 stays the same. 0, 0, 1, negative 3/4, 0. We're adding row 3 to row 2, so it's 0, 1, 0. This becomes negative 3/4 minus 2/4 gives us negative 5/4. That's 0 over there. And then we get 1/3 times row 3 plus row 1. This is 1, 0, 0. We get negative 1/4 plus 0 is negative 1/4. This is 0. This is our scratch work we don't need. So now let's see what we have. We have x sub 1 minus 1/4 x sub 4 is equal to 0, which implies that x sub 1 is equal to 1/4 x sub 4. Let's go ahead and look at the second one. This is x sub 2 is equal to 5/4 x sub 4, right? Are you with me there? And then that last one, x sub 3 is equal to 3/4 x sub 4. So, since they all have a fourth in them and we have infinitely many solutions, so here, let x sub 4, I'm just going to try to make the number smooth. Let x sub 4 equal to 4. So if x sub 4 is equal to 4, that implies that x sub 1 is equal to 1, x sub 2 is equal to 5, x sub 3 is equal to 3. Right? So if that be the case, x sub 1 is equal to 1. So this was here. So we have C3, H8, plus x sub 2 gave us 5. So this is 502. That produces x sub 3 gave us 3. So this is 3 times the CO2. And x sub 4 we said was 4. So this is 4 waters. Okay. Now, that's just using the linear algebra. Now, granted, when we were in chemistry, we had some simple techniques to get that. And you could, and you can. But woe unto you if the chemical reaction is very big. And there, it might be helpful to use linear algebra. To use linear algebra where you get the system reduced, or you put the system into a matrix and then you can solve it using something like this. But we'll talk about this guy and how to use this to solve all of these guys in a little while. Okay. Any questions on that? Okay, for the next problem, time is getting close to end. There's one other problem that I want to cover. So let me just give you the answer to this one, and you can just do this in your spare time. If I'm correct, you have x sub 1 CH3 COF plus x sub 2 H2O produces here x sub 3 CH3 COH plus x sub 4 HF. So here for this guy, you set everything up. It's for the carbon, for the oxygen, hydrogen, oxygen. Yep. You're going to end up with, once you solve all of that, they're all equal to 1. Well, you work that out and see what happens. All right. Use linear algebra to interpolate a polynomial. 2 examples here. Let me go to the larger one. Here, find the quadratic, for the first one, find the quadratic polynomial whose graph passes through the points. So you want to end up with some polynomial looking like a0 plus a sub 1 times x plus a sub 2 times x squared. Okay. I'm going to go on down to this big one because that's a cube function, so there's more to do there. This one is pretty straightforward, not as much work involved as this one down here. So let's see what they're talking about. So if we take the first point, -1, -1, so we have p of -1. I'm going to plug in x, this is like x sub 1, y sub 1, right? So I'm going to plug in the value of x sub 1 into the polynomial where I have x, and what that gives me is a0 minus a sub 1 plus a sub 2 minus a sub 3 is said to equal to -1. The y value is -1. Right? The next point, 0, 1. So we get p of 0, plug in x equal to 0. So I get a0, all the other terms go out, that's equal to 1. The third point, 1, 3. So we get p of 1, plug in x equal to 1 into this polynomial. So we get a0 plus a sub 1 plus a sub 2 plus a sub 4 is equal to 3. Then the last one, x is 4, y is -1. So p of 4 is equal to a0, this is plus 4 a sub 1 plus 16 a sub 2 plus 64 a sub 4 is equal to -1. And we should be able to produce a matrix from this and then just solve the matrix. So here, a0 is 1, the coefficient, right? The coefficient here for a sub 1 is -1. The coefficient here for a sub 2 is 1. The coefficient for a sub 3 is -1. That's equal to -1. All we have for the second equation is 1, 0, 0, 0 equal to 1. The next one, all the coefficients are 1, and that's equal to 3. And the last one, we get 0, the coefficient is 1, is a sub 0, and then this is 4, 16, 64, and -1. Any questions there? So now we solve this guy. So we come here. I'm going to interchange rows 1 and 2. And then we use that leading one to get zeros all below. And we do that. We have negative row 1, plus row 2, negative row 1, plus row 3, negative row 1, plus row 4. So we get 1, 0, 0, 0, 1, 0, negative 1, 1, negative 1, negative 1, 0, 1, 1, 1. This is negative 1 minus 1 is negative 2. And then this is negative 1 plus 3 is 2. 0, 4, 16, 64, negative 2. I'm going to take that last row, and they're all divisible by 2 without getting a fraction, so just divide everything there by 2. Add row 2 to row 3 while we're at it. Zero, 2, 0, 0, 0, 2, 8, 32, negative 1. And you can clearly see that this was A naught, A1, A sub 2 is going to equal to 0. Right? This is 2 times A sub 2 is equal to 0. So you're going to get automatically A sub 2 is 0. So that's good to know. And so what you can do is just say 1/2 times row 3, and then we're going to say 2 times row 2 plus row 4. That'll give us a 0 where that 2 is there. So 2 times row 2 plus row 4. So this is 10, 30. It's negative 4, and minus 1 is negative 5. I think we have enough to really solve. You can simplify it a little bit more if you want. I'm going to say negative row 3 plus row 2. I'm going to get a 0 there. And then divide row 4 by 5. And then I think from there we should be able to extract the answer. Well, if you want, we could take this 1, let's negate row 2, and say negative 2 times row 3 plus row 4. I think we got what we need. Let's see. This tells me that A sub 1 is equal to 1. Well, it's A naught is equal to 1. That second equation tells me that A sub 1 plus, I didn't finish simplifying it, plus A sub 3 is equal to 2. This is what A naught, A1, A2, A3. Yes. This is A naught, A1, A sub 2. So A sub 2 is equal to 0 from here. And then I have 6. A sub 3 is equal to negative 1. So I get A sub 3 is equal to negative 1/6. We take negative 1/6, plug it in for A sub 3. We solve for A sub 1. So A sub 1 minus 1/6 is equal to 2. A sub 1 is equal to 1/6 plus 2. That's 13 over 6 for A sub 1. And we can write the polynomial. We know what A sub naught is. It's 1. A sub 2 is 0. A sub 1 is 13 over 6. And A sub 3 is negative 1/6. So let's go up here. So we got A naught is 1. A sub 1 is 13 over 6. A sub 2, that was 0. A sub 3, is that the negative 1/6? So we just replace those values there and we write the polynomial. A sub naught is 1. A sub 1 is 13 over 6, was plus 13 over 6 times x. A sub 2 is 0, so there's nothing there. Then it's minus 1 over 6 times x to the third. Okay. Now, the one above that is a quadratic one, so the highest term it has is x to the second power. So I have finished 1.9. Should be able to complete the homework online and all the homework before. And so on Wednesday, I believe we're out for the holiday on Monday. So on Wednesday, when you come back, section 1.10 is very short. Take about 5-10 minutes to cover that, and then I'll review for the test. And then our test will be on, I think that's the 17th, October 17th, that following Monday. Okay? Thank you. And don't get your movies mixed up with your math, okay? And learn that from me today.